Okay, so the final example that we're looking at to do with pulleys. So a particle of mass m kilogram rests on a smooth plane inclined at an angle of 30 degrees to the horizontal. It's connected by a light inextensible string passing over a smooth pulley fixed at the top of the plane to a particle of mass 4m kilos which hangs freely. Find the acceleration of the system when it is released from rest, the tension in the string, and also the force exerted on the string by the pulley. Right, so we have got an inclined plane, 30 degrees. We've got pulley on the end, and from that pulley dangles a 4m, call that B. We've got a 4g weight there. And then over here, connected to the pulley, I've got A. So once again, I forgot to change the colour. So the tension's acting there. I've got a tension here, equal and opposite. I've got the weight of A acting entirely downwards, which is what have I done there now? mg. That should be 4mg, shouldn't it? That's 4mg. mg. I have my normal reaction there. It's a smooth plane, so I don't have to worry about any friction acting there. Now with this one, it could move in either direction. That could slide down and that could rise, or it could fall the other way. The fact that that is so much heavier means that I'm going to take that to be the direction of motion. Now if that was wrong, all that would happen is you would end up calculating a negative value for A, because it's moving in the opposite direction to the signs that we've set up. If that's 30 there, then I know that that is 30 there, which I'll use when resolving on the inclined plane. So for particle A, Newton's law will apply. So N2L horizontally, T minus mg sine 30. So that's the opposite the 30. So this is the one where the component changes from cos to sine. So T minus mg sine 30 equals ma. Equation 1. We're also going to have equilibrium here. So the sum of the y forces will equal 0. I haven't put my little reference show what's happening. So plus x, direction of motion, plus y at the plane. So r minus mg cos 30 equals 0. I haven't got to worry about an f equals mu r because it's a smooth plane. And then for B, Newton's second law, motion down, 4mg minus t equals 4ma. Right, what do they want? They want the acceleration of the system. So the acceleration of the system can come directly from 1 and 3. Don't need the second equation really, because we don't need a frictional force which is linked to that reaction. So by adding 1 and 2 together, 1 and 3 together, t's are going to cancel. I'm going to have 4mg plus mg sine 30. I know, I'll check, sine 30 is a half. Yeah, so sine 30 is a half, so that's going to be 4mg minus a half mg. Equals 5 MA. So the M's can cancel because there's one in each term. So go, go, go. 4 minus a half is 3.5 G over 5 equals A. So 3.5 6.86. So to two significant figures, A is going to be 6.9 meters per second squared to SF. Okay, so I've found the acceleration of the system when it's released from rest. The tension in the string, so I'll get the tension in the string from 1. So in 1, T minus 0.5 G equals 0.5 mg. That should be, shouldn't it? T minus 0.5 mg equals m times 6.86. So T equals 6.86 m plus 0.5 mg. So it's going to stay in terms of m, and it's going to be 6.8. Half of 9.8 is 4.9. So add 4.9 to that, and I get the tension is 11.76 m. So two significant figures is 12 m newtons. So that's the tension in the string. And then the final bit, which gets the messy bit, is the force on the pulley. So what we've got this time is, here's my pulley. I've got tension going down there. I've got a tension which is, if you think of the Z angle there, going to be 30 degrees below the horizontal. So that's 30. And then my equal and opposite force is going to be up there somewhere at an angle of theta, or splodge as that looks. System's in equilibrium. So therefore sum of the x, and we'll just have plus y and plus x as we normally would. So the sum of the x forces would be r cos theta minus t, and that would be cos 30 equals 0. And then in the y components, r sine theta minus t, that's all acting downwards, minus t sine 30 equals 0. So it looks as if I know what t is, remember, so I've got two unknowns, r and theta. You need to be recognizing that when you've got something like this where sine and cos is the unknown, the way to deal with that is by ending up with tan. So if I rearrange number 2 to get the then I get t plus t sine 30. Well, I can take out t as a common factor. So our sine theta is t 1 plus sine 30. Call that number 3. And then from equation 1, I get r, cos theta, running ahead of myself, equals t cos 30. So just taking that to the other side. So now I know my sine over cos is tan, the r's will cancel, the t's will cancel as well. So if I do equation 3 divided by equation 4, I get, let's write it all out so you can see what I'm going to do. So r sine over r cos, the r's will cancel, and on this side the t's will cancel, so that tells you that tan of theta equals 1 plus sine 30 over cos 30. So tan of theta is whatever that comes to, so fraction 1 plus sine 30 on the top and cos 30 on the bottom, so 1.732 which has probably got a third form. Yeah, it's root 3. Okay, so that's root 3. So theta is shift tan of that, of our answer, which is 60 degrees. So the force that's going to counterbalance the two tensions is going to act at 60 degrees above the horizontal, and then I want to find out the magnitude of that force. So I'll go into equation 1 is the simplest. So in 1, r, which is what I want to find, cos 60 equals t, which I know is 11.676 m cos 30. So r will be 11.76 cos 30 m over cos 60. Right, fraction 11.76 cos 30 over cos 60 equals that, can't see that, hold on, 20.368, etc, etc, etc. We're going to round to two significant figures, which will be 20 m newtons to SF. So once more, it's the resolving that which turns out to be more work to get the force acting on the pulley than the Newton's second law stuff as well. So that's it. That's all the examples that we're going to look at on pulleys.